Welcome back. We have been discussing thermodynamic functions in terms of canonical partition function and hence molecular partition function. The various thermodynamic functions that we have discussed so far include Helmholtz function, enthalpy, pressure, entropy. Today we are going to discuss another very important thermodynamic function, that is the Gibbs function or Gibbs energy. In chemistry, whenever we talk about spontaneity of a process, the first answer that spontaneously comes is that a process will take place spontaneously if the value of delta G at constant temperature and pressure is negative. Please note, if we just say that the value of delta G should be negative, then the process is spontaneous, then that answer is incomplete. The constraints must be specified, that is, for a spontaneous process, delta G at constant temperature and pressure should be negative. Similarly, whenever we talk about the spontaneity in terms of properties of system alone, we need to provide the constraints. For example, if we talk in terms of Helmholtz function, delta A at constant temperature and volume should be negative for spontaneous process. So therefore, it is important to specify the constraints. Today we talk about Gibbs energy or Gibbs function. How do we define Gibbs energy? The answer to that comes here, that Gibbs energy is defined, or Gibbs function is defined in terms of enthalpy and entropy. If someone asks you a question, what is Gibbs energy or what is Gibbs function? The straight answer is that Gibbs function or Gibbs energy is G is equal to H minus Ts. As usual, this G, H or S, these are system properties. Now, sometimes we transform an equation into another form which is more useful in the sense that the properties that we want to discuss or the equations that we want to establish become easier. For example, here when I say G is equal to H minus Ts, I can write H equal to U plus PV. This is for H minus Ts is already there. So now the new form of this is U minus Ts plus PV. I am just rearranging it so that we can recognize this U minus Ts, which is Helmholtz function. That means I can now define G also as G equal to A plus PV. We have now Gibbs function in terms of Helmholtz function and pressure and volume. Keep in mind that the changes in Gibbs function and the changes in Helmholtz function provide very important information. Revisiting that, the change in Helmholtz function is a measure of maximum work that you can draw from a system, and the change in Gibbs function is a measure of maximum non-pressure volume work that you can draw from a system. and here you have an expression which can connect both delta G and delta A, and the connectors are these changes in pressure and volume. All right. Now, on the same lines, that when we want to connect with the canonical partition function, we usually will refer to the 0 point value. For ideal system, for ideal gas, PV is equal to nRT. So therefore, I can write G is equal to A plus nRT, or G at absolute 0 is equal to A at absolute 0. Why did I do this? Because as I have always been saying, that when you want to derive certain equations, you may take a route which gives you that equation easily. And in this case, if I use the properties of ideal gas, I am able to establish this, that G0 is equal to A0. That means now I can write another equation, that is G minus G0 is equal to A minus A0 plus PV. I am just connecting this with this G, and look at when I write with reference to their 0 point values. Now what I need is, if I want to now connect this G with canonical partition function, then I need an expression for pressure and I need an expression for volume. Remember that we already have derived an expression which connects A with canonical partition function and which connects P with canonical partition function. And what are those equations? Let us take a look at. A minus A0, we have already derived, is equal to minus KT log Q. K is Boltzmann constant, T is temperature in Kelvin, and Q is canonical partition function. We have also derived an expression which connects pressure with canonical partition function. Here pressure is equal to KT into partial derivative of log Q with respect to volume at constant temperature. So now, if you substitute A minus A0 value over here and pressure expression over here, what you get is this expression. G minus G0 is equal to minus KT log Q plus KTV. This V volume comes from here into partial derivative of log Q with respect to volume at constant temperature. So here we have expression which connects G with capital Q, which is canonical partition function, and hence for a given system we need to establish whether the system consists of distinguishable molecules or indistinguishable molecules, and then we have to use this expression accordingly. Now, as I said that A and G, they are very useful thermodynamic quantities, because not only delta A and delta G give information about maximum work or non-pressure volume maximum work available from the system. But the changes in A and the changes in G can give you a lot of information. For example, let us have a short discussion. If I start with A is Helmholtz function or Helmholtz energy. A is equal to U minus Ts. So I have dA is equal to du minus Tds minus SDT, or dA is equal to du is equal to Tds minus Pdv minus Tds minus SDT. Right, this Tds minus Pdv comes from du. Tds cancel, so I have dA is equal to minus Pdv minus SDT. As discussed in the previous lecture probably, that from this equation now we derive two further equations. One is that pressure is equal to minus partial derivative of A with respect to volume at constant temperature. This is one definition. And the second derivation is partial derivative of A with respect to temperature at constant volume is minus S. And then if I start with G is equal to H minus Ts. For some advancement, dG is equal to dH minus Tds minus SDT, and we keep on further expanding. dH, H is equal to U plus PV plus Tds minus SDT. Extend it further, I have dG is equal to du plus Pdv plus Vdp plus Tds minus SDT. No problem. So dG is equal to, now in place of du I will use fundamental equation Tds minus Pdv plus Pdv plus Vdp plus Tds minus SDT. You have Tds cancelling with Tds, Pdv cancelling with Pdv, so I have dG is equal to Vdp minus SDT. So therefore, pressure derivative of Gibbs function at constant temperature is volume, and temperature derivative of Gibbs function at constant pressure is minus S. As you will notice that such equations allow you to obtain pure thermodynamic definitions of some quantities, thermodynamic quantities, in terms of different derivatives. For example, look at here, the entropy can be defined as temperature derivative of Helmholtz function at constant volume, and at the same time entropy can also be defined as temperature derivative of Gibbs function at constant pressure. So therefore, when we have expressions connecting Helmholtz function and expressions connecting Gibbs function, with canonical partition function, then what we have is, then we can also obtain entropy, volume and some other thermodynamic quantities in terms of canonical partition function through such correlations. Okay. Now, if we selectively consider only gas, let us say we selectively choose only gases. For gases, PV is equal to nRT. When I write PV is equal to nRT, that means I am assuming that the gas under consideration is an ideal gas. So therefore, if I choose to work with ideal gas and consider this equation, A minus A0 is minus kT log Q, and I substitute minus kT log Q, and then I have plus nRT. In place of PV, I am using nRT. And further, if I choose to work with monatomic perfect gas, then as we have been discussing recently, that we need not consider rotational and vibrational contributions, and for the sake of discussion, we can also exclude electronic contributions under normal conditions of temperature. And secondly, indistinguishable molecules or atoms. That means I will write Q is equal to Q raised to the power n over n factorial. These we need to now consider. So therefore, for discussion ahead, I will choose this equation and then use Q is equal to Q raised to the power n by n factorial and then proceed further. Okay, let us carry it forward. That is G minus G0 is equal to minus kT log Q plus nRT, minus kT log Q plus nRT, and we will use Q is equal to Q raised to the power n over n factorial. Indistinguishable molecules. Okay, let's proceed. G minus G0 is equal to minus kT log Q raised to the power n over n factorial plus nRT. Let us continue. G minus G0 is equal to minus kT log Q raised to the power n plus kT log n factorial, because n factorial is in the denominator, plus nRT. G minus G0 is equal to minus n kT log Q plus kT. I will use Stirling approximation. Log n factorial is n log n minus n plus nRT. Proceeding further, G minus G0, nk is equal to nr. We have discussed many times. nRT log Q plus nRT log n minus nRT plus nRT. This nRT go. So therefore, I have G minus G0 is equal to minus n RT log Q plus n RT log N. I will take minus nRT as common, and once you take that as common, you have this expression G minus G0 is equal to minus nRT log Q by N. It is worth noticing here that we started with Gibbs function in terms of canonical partition function, and when we end up it connecting with the molecular partition function, what we have in the expressions is number of moles, gas constant, temperature, molecular partition function, and the total number of molecules, atoms or particles. Now remember that this is the molecular partition function, and since we have decided to initially apply it to monatomic perfect gas, therefore this molecular partition function is equal to the translational contribution to the partition function. All right, this obtained equation into another. How is that? So I have G, let me write G by N minus G by N, G0 by N is equal to minus RT log Q over N into Na. What I have done is I have divided both the sides by the number of moles, and I have converted the total number of particles or total number of molecules as number of moles into Avogadro constant. So G by N is the molar Gibbs function minus molar Gibbs function at absolute 0 minus is equal to minus RT log Qm by Avogadro constant. Right, it is much easier if we deal with the molar properties, because then we don't need to worry about the size of the system. So therefore, the equation which connects the molar Gibbs function with molar partition function is Gm minus Gm naught or Gm0 is equal to minus RT log Qm by Na. Okay, if you want, you can leave in terms of the actual size of the Gibbs function, and as I said, sometimes it becomes very helpful when you compare the molar properties, and then you divide by N, you can discuss in terms of the molar Gibbs function. All right. So what we have is now Gm molar Gibbs function is molar Gibbs function Gm minus Gm0 is equal to minus RT log Qm by Na, and standard states we have discussed many times. What is a standard state? Substance should be pure, temperature can be any, pressure has to be 1 bar. Right. In standard state, Gibbs function in standard state, molar Gibbs function will be written like this. Okay. Pressure is equal to 1 bar, temperature any, substance in pure form. And if I apply this condition, the new equation that I develop now in terms of standard state is Gm0, Gm naught minus Gm naught at at 0 is equal to minus RT log Qm naught by Na. Just note down these differences which I have put naught. That means pressure is 1 bar. What is the significance of putting this condition of standard state over here? Is that when I utilize this equation, when I use these equations in future to connect with other thermodynamic properties, then it becomes E0. Then it becomes easy. For example, it becomes very important to understand the meaning of delta G naught and the meaning of delta G. Always distinguish between delta G and delta G naught. Delta G naught is connected to equilibrium constant by minus RT log K. Now you will be able to appreciate that if at a later stage I need to connect Gm naught or free energy Gibbs function under standard state conditions with equilibrium constant, then I need an expression in terms of Gm naught. That is the reason we have now expressed this in terms of standard state, so that any differences in the value of molar Gibbs function under standard state conditions can be connected with equilibrium constant. So I hope that the discussion on Gibbs function and its relevance has been useful, and here we demonstrate that we can get Gibbs function or molar Gibbs function from the value of molecular partition function, that is from spectroscopic observations. Thank you very much.